Hello, my name is Marissa Tucker. I'm the product marketing manager for both the Control and HMIs based out of beautiful California. Today I want to talk to you about Ethercat basics. If you're interested in Ethercat, this is going to be a great webinar for you, as this will be predominantly a technical presentation. Of course, we will allude to the Parker Pack product, but anyone who is interested in Ethercat will benefit from watching this webinar. So before we get into Ethercat and how it functions and why it's such a great protocol, we really need to understand what else is on the market and how the vast majority of protocols actually work today. Most of the protocols that you see in the industry today, whether that be Profinet, Ethernet IP, all of it is based upon Ethernet, which one could argue is the backbone of our internet structure. So let's just get a feel for how that works. So we have two devices here. So the first device says, we'll just call it device A, hey, you want to chat to device B. Device B has to make some confirmation saying, hey, yeah, sure, I'm up for that. Device A then says, hey, great, I'm going to confirm we now have this established connection. Now device A wants to actually go ahead and send some data to device B. Device B, once it receives that data, has to respond back saying, yes, not only have I received this data, but I've checked this data and this data looks good. Now device A says, okay, I actually need to send you a ton of data and it doesn't fit all into one single message. So I'm going to have to send you multiple messages. So device A go ahead and starts with packet 3. Device B again has to go through and check the data, make sure that everything looks good, and confirm to device A that it received that data. Device A sends the next packet, and again device B, wait, what happened here? So device B doesn't respond in this case. Maybe it didn't get the message. So what device A is going to do is it's going to resend that exact same packet again. Now, device A is only going to move forward after it gets that communication from device B saying, hey, I checked the data and it looked good. So it looks like we've reestablished communication. And then of course we want to send the last packet from device A, and again device B says, hey, everything looks good and we're good to go. So device B is going to be responsible in this case for taking all of that different parsed data and making sure that it's in the right order for use in the application layer. So then device says, hey, I'm out of this conversation. I've sent you everything that I needed to. Device B then closes that connection. Okay, so say with Ethernet TCP/IP, device A sends a packet to a slave and says, hey, here's the updated data, and I don't receive anything back from device B. Well, now I've just gone through a few servo cycles and finally device B goes, oh, by the way, here's finally my response from something that occurred 5 or 6 servo cycles ago. That's just not an acceptable way to operate our control scheme. So the alternative is looking at something like Ethernet UDP/IP. TCP/IP is predominantly going to be used when you want to make sure not only that the data gets there, but the data gets there correctly and in the right order. So an example of where you might use TCP/IP might be like a firmware download. Ethernet UDP/IP is going to be a little bit more familiar and what you would most associate with a control network. In UDP/IP, both devices need to know what type of packet is going to get sent from one to the other, what that data means, and how to parse it out. So initial configuration actually has to go on both devices. This would be something like your electronic data sheet or your EDS sheet in Ethernet IP. Even though Ethercat doesn't work on a UDP/IP, you could also say that this is kind of similar to what you do with the device configuration files. So how does this operate differently? Basically, device B just starts blasting data to device A, saying, hey, I'm sending you data. Now, after a certain set amount of time, in this case 500 milliseconds, device B sends that exact same data packet again. And after 500 milliseconds, it sends that data again. In this case, because we're not communicating unnecessarily, we're not confirming that the packets have gotten there, it's a lot more bandwidth efficient. The master has the additional responsibility of not only parsing out the data, figuring out what it means, and making sure that it's okay. All of a sudden, processing speed becomes very, very important. Because right now we have a single connection from 2 devices, but imagine if I have 50 slave devices on my network. The processor speed of the master not only determines how many slave devices that you can connect up to, but it also determines how quickly you can communicate to each one of those slave devices. So again, kind of bringing this back to the Allen Bradley realm, It really is kind of your difference between your regular scanner and your ultra high precision scanner. While you might see a lot of proprietary protocols out there, the vast majority of them are still running on Ethernet, TCP, IP, or UDP. Ethercat is totally different and completely unique. I just want you to kind of visualize Ethercat as a train, specifically a subway train. When you look at a subway train and you look at its network, the train knows exactly where it's coming from and where it's going when it arrives at the station. There's only one in and there's only one out direction, right? That means that I do not actually have to be fully processed as a packet. So usually when I send information to a device, remember like in TCP IP, there's some sort of confirmation that I received it. So the entire packet has to fully be read and analyzed before there is a response or before I forward that packet further on. So as data packets are coming in on the Ethercat import, they're immediately being written on the output. The other reason why this is possible is because the data is going to be written at a very, very specific location. Let's say that the data that we're trying to transfer around is people. And so they know what stop to get on and they know what stop to get off. So Ethercat is very much in the same way, where it has designated locations along the packet where your first device would be written to, and it has very specific places in its packet where device 1 knows that it's going to read from. We can just simply pass the data, and I can simply just count the bits by and say, oh, this is where I write to. And likewise, oh, this is where I read from. And the rest of the packet we don't care about. So we're actually not processing anything as the packet is coming through. In Ethercat, there is no stopping. So you can imagine in a subway system, it's like people running up and throwing themselves into the train. But that's really what's happening. Another similarity for Ethercat to the subway station analogy is because I leave from a single station, I go along my route, and I come back. That is exactly how Ethercat works. It sends the train from the master, it goes the same exact route every single time, and then returns back to the station. So what you also get as a huge benefit is so much additional bandwidth for the data that you actually care about, since it strips off all the unnecessary layer of checksums and header information that are really not useful to Ethercat. But what it also does is, because we're using this train-like packet structure, that means that there's absolutely zero chance for collisions. So I get asked a lot about Ethercat. Oh man, this is a brand new standard. I don't know about this. Well, it's actually not new. Just like a lot of new protocols that come out, our industry is really slow to adapt them. So Ethercat, believe it or not, has really been around since 2003. Ethercat is really well proven at this point. In fact, there's about 2,500 manufacturers that are part of this Ethercat group. Of course, Parker is one of them. When people mention Ethercat, yeah, it's a very unique and interesting technology, but what does it really get you? The very first thing that people start talking about is the speed of Ethercat. So this was a test that was done by the Ethercat group, which Parker is a part of, and they did a comparison test, and they said, okay, we have a 40-axis system with 50 various I/O stations. Now, each one of these I/O stations has a variety of O, but they all total to about 2,000 digital I/O and 2,000 analog I/O. So trying to create an as equal as possible system, because again, some of these protocols, in order to prevent collision, require extra hardware, etc., etc. But you can go ahead and, again, if you're part of the Ethercat group, you can read that study and see exactly how this trial was created. In fact, they tried to make the study so equal, they even made sure that the bus length, or the actual amount of copper that each of the packets had to travel, was the same between all of these networks. So given all of that, Ethercat blew the competition out of the water. To read and write to everything in the network, it took Ethercat 276 microseconds. The next closest protocol is almost double that at 479 microseconds for Circos 3. So when I show this slide, especially in North America, you get a lot of people going, oh, this is really great. I'm so glad this is fast, but how does this compare to Allen Bradley? Well, another study was done actually by a university in India. Again, I have the link here so you can read up on this on your own. Ethernet IP is operating just like UDP would be. And so because of that, it was only fair to use a variety of Allen Bradley scanner types in order to ensure a fair comparison. Given 64 connections or 64 devices on the network, using an ultra-high performance scanner, it took Ethernet IP 5.21 milliseconds to read and write from all of these devices. Given a similar network over Ethercat, 64 devices took about a little over 600 microseconds to read and write to all of those devices. So again, there is an entire order of magnitude difference between a typical Ethercat network and an ultra high precision scanner Allen Bradley product. So when you want to talk speed, there really is no comparison with Ethercat. So what does speed actually get you? Take a look at what other buses do. So as I'd mentioned, most other buses are based off UDP. Most buses have a cycle, right? They're only updating, for instance, every 500 milliseconds or whatever that particular interval might be. So there's a bus cycle associated with it. When you get an input, whatever that input device is going to take a certain amount of time to process that input. So that is designated here by TIO. If that input occurs in the middle of a bus cycle, that means that that input is just going to have to wait around until the next bus cycle in order to get registered. Once that information is on the bus, the processor of the controller is going to take some time in order to process, and that's shown here as the master processing delay, or TMPD. If that information is retrieved from the bus cycle in the middle of a PLC task, that means it has to wait for the next PLC task to get registered. So we're talking about potentially up to 2 PLC tasks that could have already occurred before we've even registered an input. And this is also the same process that happens on the output. So your best case reaction is probably within a few PLC cycles. So that means the best possible reaction time that you can have is dependent on how frequent and how fast you're running your bus cycle time, and how frequent and how fast you're running your PLC task. Well, we already kind of knew that. We knew that PLC systems weren't perfectly deterministic. That's where Ethercat changes this conversation. So with Ethercat, we're running the Ethercat network in between your PLC cycle task. So what that ends up looking like is this. All of a sudden, your worst case scenario ends up looking like the best case scenario of running a whole separate bus cycle. And that's why I say if determinism is important to you, and as a controls engineer, that should be, you need to be using Ethercat. But how many devices can you have? And what they're really saying is, well, how many motion control axes can I have? Well, the answer is really the same. You can have 2 to the 16 of whatever you would like on the network. And in case you want to do the math, that's 65,536 possible devices that you can have on a single Ethercat network. So have we had 200 plus axes controlled by a single pack? The answer is yes, absolutely. And because Ethercat is still based upon the Ethernet physical layer, that means that it can handle 100 meters in between devices. So not only can you have as many devices as you could possibly want on a machine, this also means you can have an extremely large machine. As long as there is an additional Ethercat device or node in between those distances, you'll be fine. So what kind of hardware is required in your system for Ethercat to run? The answer is none. There are master and slave chips on each of the Ethercat devices that you purchase, but we're talking about itty-bitty tiny chips. So in terms of added cost to your PLC device or to your slave drives that you might have, it's really not substantial. But all of that, again, is going to be taken care of for you by the manufacturers. So there's no other additional hardware that you would need to consider. So the price of the device that you're buying, that's really the price of the network that you're investing into. So what kind of physical networks are supported on Ethercat? All of them. Star, line, tree, ring, whatever your heart possibly desires. So the nice thing is that it is able to achieve this by a very basic hardware set. So you go out the out port and you plug into the next device's in port. You go out the out port and you plug into the next device's in port. Now, as long as you follow that rule, you will be good to go, and you cannot wire Ethercat incorrectly. It really is one of the few protocols that would say are truly a plug and chug protocol. But the reason I call it a plug and chug protocol is, well, not only is it very, very simple to wire, but you also do not have to do any addressing. And remember, especially the old school way of addressing, having to set up an Ethernet IP address for every slave device that you have, it's something that truly could take hours depending on the number of devices that you have. So the nice thing with Ethercat is it boots up and it addresses everything for you. So how is this possible? Well, let's take this particular physical network as an example. We've gone out the out ports and in the in ports. So let's see what Ethercat does. How does our train flow through this network? So the very first thing that happens is that the Ethercat master, which in this case is the pack, boots up and goes, hey, I am the master of my universe. I'm going to send out a packet out of my port 0 and see if that there's anything out there. So the very first port it goes out of, trick question, is actually the pack IO port on the side of the pack. And it goes ahead and it addresses each one of those items as 1 and 2. Now it keeps going until a device does not have a connection on its out port. When that's the case, it returns all the way back to the first junction. So then it goes, okay, well, I found all the devices on my port 0. Now I'm going to go out and find all of the devices that are on my port 1. So it goes out port 1 and it continues to address every single device it finds up until it finds a device that has nothing connected to its out port. So then it returns all the way back to the most recent junction, increments the port that it goes out of, and follows that line until it finds a device that there is nothing on its out port, and it returns all the way back to the original junction. And if there's no additional out port on the pack, which there is not, it goes, hey, great, I addressed the entire system. As it was going through this process, not only was it addressing everything, but it was also mapping the entire system. So when we send an Ethercat train packet out from the pack, it'll actually follow this exact route every single time. So one of the most underappreciated aspects of Ethercat is distributed clocks. Distributed clock is really important because it allows each of the drives to coordinate the execution of motion commands across a bus. This is possible because remember we said that every single device has an Ethercat slave chip in it. Well, some of these Ethercat slave chips have the ability to basically sync clocks between each other. And this is a hardware interrupt sync pin on each individual slave device. The great thing is there's actually no configuration required to set up distributed clocks. This actually happens completely automatically. So when we say that there's substantially less than 1 microsecond of jitter between slaves, what we're really saying is how closely in sync those slaves are executing their motion commands with each other. So distributed clocks are really, really important when you're doing any type of coordinated motion. So this can be as simple as gearing and camming. It could also be if you're trying to do any type of three-dimensional vector motion, and of course, especially when you are doing any type of robotic or CNC control of a system. So how does Ethercat actually accomplish this? How does it actually sync up its clocks? First thing that the pack does is it boots up and it addresses everything downstream. It also sets the reference clock as the first slave drive that supports distributed clocks. Then what it does is it sends out a packet very similar to our addressing packet. But instead what it's doing is it's recording how much time it takes to leave and arrive at each individual device on the Ethercat network. Now, once it's timed everything, it's able to calculate propagation delay. Propagation delay is simply the amount of time difference it takes for one device to receive a command versus how long it takes the next device to receive a command after it's left the master. Now again, this is really important because our Ethercat train packet is not going to arrive at each of the individual drives at the same time. Especially when we're looking at coordinated motion, we want to make sure that all of the devices have received their command before they execute. So measuring that propagation delay is really important. The pack also tells each of the devices what its propagation delay is so that they can store that information. Now the pack says, hey, I'm actually the master in this situation and I know my own propagation delay. So what it's able to do is set the reference clock to its specific time. And it does this for all of the slave clocks. Now note, when the master clock is setting the slave clock, it is setting it for the time it is going to be when the packet actually arrives at that slave device. So that way, after all the slave devices are set, they're all on the same clock. A little review here. Now remember, we're running the Ethercat bus in between our PLC task. Now the reason that this is important is that, remember, we want to make sure that all of the slave devices receive its command before it executes. We actually want our sync trigger to happen well after the Ethercat read-write cycle has occurred. So in Parker Automation Manager, you can actually set when the sync actually triggers. There is, of course, a default that works in most applications, but this is just something to be aware of. And it's set as a percentage of the overall update rate that you select for your PLC task. So to give you guys just a brief little summary, because there's a lot of both technical and general information that we covered for Ethercat today. Ethercat is a well-adopted standard that's actually been around since 2003. And of course, there is no comparison. Ethercat across the board, it is the fastest protocol available today. And don't forget, for that speed, you get a much more deterministic cycle on your bus network. In addition, Ethercat handles all of the addressing for you. You just have to remember to go in the in port and out the out port, and you can do no wrong. Ethercat also handles all of the distributed clocks for you. And if nothing else, remember that Ethercat allows you to do high precision motion control on a bus. All right, well, thank you very much. And if you have any additional questions, please feel free to open up a chat and reach out to me. If you're watching this on YouTube after the fact, feel free to reach out to me either on my LinkedIn page or in my email contact information below.